Right, morning. My name is Christopher, and I'll speak to you a little about satellite video remote sensing and its application in flood hydrology. So, although my affiliation this morning is with the University of Glasgow, which is where I completed this work during my PhD last year, my current affiliation is slightly different right now. So it's with a global reinsurer who's based in London, and I work as a catastrophe risk analyst for them. But in this case, I will just be presenting some work from the PhD. So the work today is entirely based upon two papers, which are quite recently published. So there's the one, Water Resources Research, that was published in January of this year. And then there's the sister paper from Geophysical Research Letters, which was published in December of last year. So for this talk, there's no way I'm going to be able to sort of talk about all the technical detail of these papers, but if you want to have a deep dive into things, feel free to come and have a chat with me. And there's an entire piece as well, which goes into a bit more depth, and another paper which just sort of adds to what we did here with some separate experiments in the UK. Right, so as we all know in this room, floods are the most frequently occurring natural disaster, and they account for a disproportionate amount of economic losses when you think of natural catastrophes. And therefore, it's really important that flood model predictions are delivered with a degree of accuracy. And that's pretty much where satellite video remote sensing comes into play. So satellite video really is a step change in our ability to study flood dynamics as compared to still satellite imagery, which a lot of you here have used, and there have been a couple of examples here of people talking about Lancet, the Sentinels, the MODIs, but full motion video, which we now have ability to acquire from space, can enable us to study evolving phenomena such as floods in this instance, and that's what we were doing here. So at present, all satellite video remote sensing missions are commercial, and they're acquired by three main players. So the first player is Planet, who are based in the States. There's the Chinese Changwon Satellite Technology Limited, and then it's the UK Science Technology Limited. And in this instance, we went to the Chinese satellite video provider for a couple of reasons that I'll explain later. But essentially what these guys do is they operate a constellation of satellites which are in low Earth orbit, and they acquire full motion video, which is pretty useful when we think of deriving velocities directly from space, which hasn't been demonstrated before, and we were able to do this. Guy Fluor, I know he's seen this presentation before, part of it because I presented it in Vienna a couple of months ago during the interview, but I've just extended it a bit, and it's good to be presenting it at home as well, because yeah, and as well. Right, so we'll look at it in terms of two applications. So the first one is the use of satellite video for flood model validation, and then the second is the use of satellite video for estimation of river discharge directly from space. So when we think of flood model simulations, these are typically, they are usually assessed using one of three data sets. So you can either use observed flood depths, which come from water level ages or estimate emission. You could also use observed flood extents, which a lot of studies do. Use Lancet, Sentinel, right? And then you could also next commonly use observed flood velocities, which are a lot more challenging to acquire, especially during high discharge events such as floods. And this is where satellite video really comes to play, and that's essentially what we were doing in this study. Oops, oh, something. Right, we're back. Right, and then in the second application, thinking of satellite remote sensing the estimation of river discharge. So at present, there are really two key ways the two approaches that are mostly deployed. So one is either using still imagery, still optical imagery, or using radar data sets, and then we indirectly calculate discharge. But the difference with satellite video now is that we are able, for the first time, to directly estimate velocities without having to use either hydraulic models or approximations, which is typical with either altimetry or the optical and infrared sensors. And this is really, really key, especially in engaged catchments and in places where instrumentation is not really adequate. Those are some of the advantages that satellite video brings to play. So a really quick overview of the methodology that we employed. So essentially, this was done in 4 stages, really. So in the first stage, we extracted planning sense using a deep learning network. This was a highly encoded network that we'll speak about briefly. And then for the estimation of velocities, we used image velocimetry techniques, which is essentially cost correlation of images that have been obtained from the video. Just so you know, so video essentially is just a bunch of images which are stitched together at a certain frequency. And so you can decompose them and be able to track the movement of particles in them, which is exactly what the LSPAV algorithm does. And then we simulated a flight event, which occurred in the Tilbury catchment in Australia, which is shown to the right. This is a 105-year flight event that took place in February of 2022. And what we did is we tasked the satellite video vendor to acquire video for us. And it was really opportunistic because this is optical video. And that means just in case there's cloud cover that would have obscured our study, but we were quite lucky that we were able to obtain some cloud-free data, and we subset the video into 2 locations, so location A and B, and that is where all the model validation and river discharge estimation. Right, so moving on, like I'd say, really core to our methodology was the use of this deep learning network to do something called semantic segmentation, which is essentially pixel level identification of flags. And this can get really complex when you think of satellite data, satellite video data, because we've got both motional context and what are called static context. So the river which is moving, and then we've got land which is static. And when you think of segmenting pixels, especially differentiating, say, water from land, that can get really tricky. And so we leverage some big AI. So what we do here is we came up with a bit of a hybrid model, which uses something called a cyclone encoder, which is what you see at the top, and then at the bottom, we adapted an encoder from a network called UNET, which has been deployed extensively, remote sensing studies. And so what we do is, because the satellite video frame is really massive, we divide it into little patches, just so we can be able to efficiently use our computational resources, and then we feed it into the network. So we used something called a pre-trained encoder. So the encoder has been created in quite a popular data set called ImageNet. And then we fine-tuned the encoder using our satellite video images. And then after that, we upscale the encoded images, the decoder, and these are output, and we conduct something called test segmentation, which is the second really important part as far as segmenting this flight extent goes. So what test segmentation is really, it's a bit of a trick to enhance the generalizability of our model. So what that is instead of just letting the model infer directly from a raw image and then it give you the segmented prediction, what we do is we take this satellite image patches and then we do multiple transformation for them, which I described in the paper, but that's kind of what's depicted on the image. And once we've done those transformations, we run them through the network. We obtain predictions, and then we augment, so essentially we revert back to the original images that we had, and then we stitch together all these patches to form the full scale image that we had originally, and that's what we use when we are validating our model simulations. Moving on quickly to the estimation of discharge. So I think here the key takeaway really is we're using pretty much the same data set, and what we do is after we subset the video, the two sub-regions that I showed you, A and B, what I did was we extracted frames at married frame rates for a couple of reasons, which is explained as well elsewhere. And then very importantly, we conducted stabilization, because when this video is being acquired by the satellite platform, the platform is really in motion, and therefore there is a bit of residual motion that could be induced to our scenes, and you want to make sure that you've accounted for that. Otherwise, because you're observing the phenomena from such a far distance in space, if you fail to account for any residual motion that's caused by the satellite platform, you'll end up getting really spurious velocities, which is not what you want. So we use a scaling variant feature transform algorithm to stabilize our frames, and then we run pretty much the same exact process in an algorithm called VIVLA to estimate surface velocity, which is then depth averaged using something called an alpha coefficient, and there's a lot of studies that are taking place as far as that goes. In our case, we used some standard coefficients to convert our surface velocity to depth average velocities, which is what you want when you want to estimate discharge. And then following that, we just use the classical velocity area method to estimate discharge within our catchment. Right, so key results. One, flat extent validation. So if you look at those panels at the very top, there's the extreme left is just a satellite image patch for one of the validation sub-regions A, and then next to it two footprints from the model simulation. So there's one footprint where the model was forced using observed discharge, and then in the second footprint, we forced the model using uncertain discharge. So essentially just a content of certainty in the discharge that we were forcing the model with. And then the last two are just the deep learning-based segmentation results. So one where we employ test type augmentation, we just spoke about earlier, and then another scenario where we do not employ TTA. So we just wanted to test and see the influence of carrying out this simple trick that helps the model to perform better. And in summary, our critical success index peaked at 94%. And on average, it was around 83% across all sub-regions. And one thing we noticed as well is that whenever we implemented TTA, the hit rate declined consistently. And the reason for that is because TTA manages to remove any extra non-flooded pixels that the model might have captured. Even though the model is really good, it still is vulnerable to some uncertainties. So TTA just helped us to account for that. And whenever we deployed it, we observed that there was at least a 9% improvement in the validation metrics. Flat velocity validation using LSPIV. So those are just correlation plots for LSPIV velocities versus Equus model velocities. And what we observed consistently was that LSPIV was underestimating velocity, and a couple of reasons, but we estimate that potentially the LSPIV algorithm that we used was oversimplifying some of the catchment hypotheses, and that's the reason why we had a slight underestimation. Nonetheless, on average, we were getting R values of around 0.78, which was quite decent, and it just showed that there's an actual statistical relationship between our LSPIV velocities and the model velocities in both scenarios. So like I said, we're doing two models. So there's the one model which is MMOPS, that one's for observed discharge, And then 2 months post, where we've accounted for discharge uncertainty using some Bayesian methods. When it comes to river discharge estimation, like I said, LSPAV tended to underestimate velocities compared to a 2D model prediction across both catchments. However, our discharge estimates were roughly within 0.5 to 15% of observed gauge estimates, because we had a gauge pretty close to where we were making this satellite video acquisitions. And I really key source of uncertainty as I speak about this, and I guess that's what Guy and the other guys who are doing a more extensive study than I did for a PhD. There's an extensive study called Fluvisat that's being conducted by the UK Center for Ecology and Hydrology, and I know they are acquiring data from 3 platforms simultaneously. So that's from an ADCP, which would be the gold standard for acquiring these velocities and discharges, and then a drone and satellite platform. But the point that the tuning of this alpha coefficient, which is pretty much a value that you use to evaluate the velocity, is really sensitive, and that changes pretty quickly, depending on river discharge and depending on the channel morphology and lots of other nuances that are playing. And we speak about this in depth. However, even though we do observe this range of, like I said, between 0.5 to 50% variance between our discharges and observed discharge, there's still a lot of uncertainty that's associated with the selection of the alpha coefficient for fine-tuning our velocities. In conclusion, satellite video remote sensing, we successfully were able to derive flood extents and velocities, and we assessed the scale of a 2D model successfully. And we were also able to use velocities from satellite-based LSPAV, coupled with really high-res topography to estimate river discharges to within 50% of easy to gauge data, which we thought was impressive, if I say so. And yeah, so future work, this is already being done by UKCH, the platform simultaneous acquisition of data from all these platforms, which can be quite useful to cross-validate the data that you are acquiring from all of them. And then finally, which is something that we are kind of working on, is the simulation of this velocity and flood extent data in real time into flood models, which can be quite useful to sort of just improve focus and tune model parameters in real time as flood events take place. And I think over time, as these sensors get even cheaper and a lot of nano-satellite missions are being launched, we think satellite video is going to become a lot more common and a lot cheaper because it's pretty expensive for now. But yeah, we hope the future holds for a lot more availability of this data for various uses. Again, those are the references that I've used pretty much throughout the talk. And if you want to have a further discussion, feel free to reach out. Thanks.
Yeah, thank you, Christopher. It was very impressive. And we have time, for 2 questions. If you want to stay here, if there's any question from the audience. Otherwise, I have one, but you Albert as well. Albert?
Yes. So thank you for your presentation. It's really, it's awesome that you can measure water discharge using satellites. I was wondering, so if I understood correctly, you're using MODUS, so optical imaging. MODUS is, you get 2 images a day anywhere on Earth. So that's good. You get a high resolution or high frequency return to it, but it's optical. So if there are clouds, you're kind of you're in the midst of what's happening and you have to wait another day, maybe another day. Did you have a method to solve that, or are you using other imagery to kind of try to fix it? Can you explain that a little bit more?
Yeah, so there's no escaping clouds for now, even though a lot of guys who work in deep learning techniques to remove clouds, but that was not the focus of my research. So like I said, it was a really opportunistic acquisition. So had there been any cloud cover, then we would not have been successful. But the reason why we chose the catchment in Australia, which is a really high latitude location, because in that catchment in the Darling Basin, whenever there's such high precision event, the sky tends to clear quickly, and the catchment is also the flood rate is pretty slow. So that's why we were able to capture it. But had there been any cloud cover, then we just wouldn't have been successful. Yeah, it's still a limitation for people.
Yeah, I have a small question, but maybe, I mean, it's because of my ignorance. Right? So I imagine, I mean, for the surface water velocity, I mean, tracking, you need, I mean, some kind of, let's say boogies or targets, I mean, that you measure. What is the typical, given the resolution you have, which is pretty high to be a satellite, but I mean, not enough, I mean, to capture maybe, I mean, fines, debris, or what is the typical, let's say, signature that you read on the surface of video that you track for the velocity vectors?
Thanks. So yeah, actually it was adequate. We were tracking so changes in one, there's a lot of sediment that was being carried by this river. So one, that's what we are essentially tracking. And the data, by the way, is freely available as well. Those who want to have access to it, the satellite video is there, and I think it's pretty cool. You can have a look at it. But Roberto, what we're doing is at sub-pixel level, the algorithm that we're using, which is called PIPLab, has the capability to detect frame-to-frame movements at something called sub-pixel level. So we are tracking sediment particles in this case, which is at the river being clear, that wouldn't have been possible. So there are bits of reflection and sediments that we use to track with the algorithm.